Alright, hello everyone. So this question is asking us to determine the appropriate hybridization of every carbon, nitrogen, and oxygen atom in these chemical structures. So let's go ahead and get started. Recall that when determining the hybridization of any given atom in an organic molecule, it's a question of how many quote-unquote groups are surrounding the atom in question. When I refer to groups, I'm referring to the sum of two different categories. I'm referring to any lone pairs of electrons, if there are any, as well as atoms, or the number of atoms that are connected to the atom of interest. Note that I'm not focusing on the number of bonds necessarily, just the number of atoms connecting to the one of interest. Let's start with the carbon atoms of the benzene ring given in this structure. If I focus my attention on one individual carbon, we can see that each one of them is connecting to two other carbon atoms inside of the ring. But recall that an unsubstituted position on a benzene ring does have an invisible hydrogen that is not shown in this skeletal structure. So really, these unsubstituted benzene carbons have a total of 3 groups because they have 3 other atoms connecting to the atom of interest. When the total number of groups is equal to 3, that corresponds to sp2 hybridization. Now, 4 groups corresponds to sp3 hybridization, and 2 groups corresponds to sp hybridization. So the benzene carbons are sp2 hybridized. And I want to point out here that this is also true for the substituted benzene carbon present in this molecule. Because even though it doesn't have an invisible hydrogen, it's still connecting to 3 other atoms when including the carbon atom of the second ring structure. So all of the benzene carbons are sp2 hybridized. So now let's talk about the second ring structure, particularly on nitrogen to start off. Recall that nitrogen has a bonding preference of only 3, with 1 lone pair of electrons to maintain a formal charge of 0. So as for the number of groups that nitrogen has, it has 1 lone pair of electrons and 3 other atoms surrounding it, namely 3 carbon atoms. This equals 4 groups in total, which corresponds to sp3 hybridization on that nitrogen. And we can see also that the remaining carbons on that ring, including the methyl group branching off of nitrogen, are also sp3 hybridized. Because if we focus on a carbon atom inside of the ring here, it's connecting to a total of 4 different groups, 2 hydrogen atoms that are not shown, and 2 carbon atoms. The methyl group is also sp3 hybridized because it's connecting to the nitrogen as well as 3 hydrogen atoms. So that's 4 groups and is therefore sp3 hybridized. Now in the center of my structure, we have yet another carbon atom. And this carbon atom is connecting to 4 other atoms, which would make it sp3 hybridized. Specifically, we have 2 carbons from the ring containing nitrogen, 1 more carbon from the benzene ring, and the other from the aldehyde functional group. So that's 4 groups in total. And last but not least, we can focus our attention on that carbon. Apologies for that. But moving on to the carbonyl, recall that this is an aldehyde. So the aldehyde carbon, specifically the carbonyl carbon, does have a hydrogen atom that's not shown. So this carbonyl carbon is connecting to one oxygen atom, one hydrogen, and one carbon atom. That's 3 groups in total since there are no lone pairs on carbon, and is therefore sp2 hybridized. Last but not least, we have oxygen from the carbonyl. Now, oxygen, to remain neutral, prefers 2 lone pairs of electrons. So that's 2 lone pairs, and it's only connecting to the carbon atom of the carbonyl. So 2 lone pairs and 1 atom connecting to oxygen means 3 groups around oxygen, which is therefore sp2 hybridized. And there you have it. Now here are the hybridizations for all atoms present in this molecule. But before we end this video, I do want to point out here that the presence of resonance, or the ability of a certain atom to undergo resonance, might also change the hybridization expected. For example, let's take an ester. The oxygen of the ester is expected to be sp3 hybridized because of the rules that we were talking about earlier. However, the lone pairs of electrons on oxygen participate in resonance with the adjacent carbonyl. So in actuality, the second oxygen of the ester is actually sp2 hybridized due to that ability of oxygen to undergo resonance. So that's an exception to keep in mind, but that did not apply in this molecule. So with that being said, thank you so very much for watching, and I hope you found this helpful.